portal for 30 minutes, how far would you actually fall? Now, I've been asked this question a lot since Thor Ragnarok came out. And in that movie, Loki is put through a magic portal by Doctor Strange. And when he is released from that portal, he says he has been falling for 30 minutes. Well, how far would you fall in that time? Or how hard would you hit the ground when you landed? Well, let's set some parameters here. Let's just assume that Doctor Strange sends Loki through a normal density air, like our atmosphere. Then, Loki will quickly reach terminal velocity for a human-shaped thing falling in a skydiver's cross-sectional area. Now, that's going to create a drag force that will get him to a terminal velocity of around 50 meters per second. Now, that's when Loki will stop accelerating. So, in 5 seconds, he'll reach this, and then he'll have 29 minutes, 55 seconds to fall at around 50 meters per second. And if you do that math, it's not too complicated. You find that Loki will have fallen in that scene around 90,000 meters, 90 kilometers. That's basically the same height as space. The Kármán line is the most common line to denote space, about 100 kilometers above the surface of the Earth. So Loki falling that distance in that time is like falling from space. But Loki also hits the ground in this scene, and he doesn't splatter. If you hit the ground at 50 meters per second, which is around 120 miles per hour, you'd be not good. So let's assume that instead of falling at 50 meters per second, that instead Loki hits the ground at the terminal velocity of 5 meters per second. Well, how could we slow down to this terminal velocity? Well, one thing that you could do that's simple is assume that the portal, wherever the dimension that Loki is going through, let's say it has air that is 100 times denser than normal air density. And I know this looks like a P, air, but it means density in engineering speak. Anyway, if you make the air 100 times more dense in the portal that Loki is falling through, then you get a terminal velocity of 5 meters per second, which you accelerate to in fractions of, in a second or two, less than 5 seconds. And then you find that at the end, when he is released from the portal, he hits around at 5 meters per second, probably lives, but he has traveled 10,000 meters, this time about 10 kilometers. Lower, so the force is lowered on him when he falls down. However, if you had air that was 100 times more dense, it implies that the atmosphere that Loki is in might be many times more dense. And if you do the math, it's like more dense than Venus's atmosphere. And if you try to open up your mouth in this kind of atmosphere, air would rush in and rip your lungs and you can't breathe and you die. So there'd be a lot of magic involved. Hello, and welcome to another edition of Because Science Live, the show where I open up with a weird and interesting calculation, and then I go to you, taking your comments and questions live off the top of my head to the best of my ability, mostly to make me a better science communicator, but halfly to entertain you. I have Nate here. What we got?
From Scott Powers, which explosion would be bigger? Our sun going supernova, or Earth being turned into pure energy via antimatter?
I do not know. Off the top of my head, the energy that supernovae, if you're nasty, the energy that they put out is orders of magnitude more than I think what it takes to gravitationally separate the Earth, like a Death Star laser would, to completely destroy the Earth and remove the pieces out to mathematical infinity. But I do not know offhand if you multiply the mass of the Earth, which is 6.0, no, it's like, yes, 6.02 times 10 to the 24th, that's a 4, and that's a 2 kilograms, and you multiply that by the speed of light squared to get the energy, as we all know, E equals mc squared. That's a giant value. So I don't know which is bigger offhand, but those are two tremendous booms. What we got next? Yeah, I mean, we could do the math really quick if someone opened up, like a Wolfram Alpha. Who doesn't sponsor the show, but I use it for everything. What's next?
From Keelan Henshaw, what keeps the Death Star from flying backwards every time it shoots? Shouldn't the opposite forces push it backwards?
Lasers are mostly recoilless, I think. And that is because when the kind of reaction that you were talking about, you typically have, if you're thinking of recoil coming out of a gun, it is because you are firing a bullet at some velocity, and to move mass away from you at some velocity, it's going to create that recoil to conserve momentum the other way. Light is photons. Photons have momentum, but they do not have mass. That's why they can go at the speed of light. That's what lasers do. So even though they have momentum, it is very, very small. It's one of my commenters on one of the videos said I think even what is it, megawatts or gigawatt lasers have less recoil than what would happen if you threw a baseball away from the ship. Something in that ballpark. So even with a massive laser, because it is photons of light which carry momentum, yes, but not mass, there wouldn't feasibly be a giant amount of recoil. Now, if the Death Star was shooting out a projectile, like firing a railgun or something like that, then yes, you would have significant amount of recoil, but not with a laser beam. I don't think. I'm sure Matt or Beam will correct me on that. What's next?
From Psycho Lesne, how strong would the Dragonborn from Skyrim shout if he can remove clouds from the sky?
I'm just getting a bunch of easy questions today. That's what I like. So, I've seen a lot of YouTubers do like how strong is the Fusro Da and stuff like that, and they just do raw decibel values and just say, oh, explosion. I don't really like that. This where sound stops becoming like a sound and becomes more like a shock wave or a blast wave, if you will, is 194 decibels. So I will say that it starts at this value because you have a shock wave of air coming out from the Dragonborn or Dovahkiin, again, if you're nasty, and you can see this visible shock wave come out from this person's body. This is more like a blast wave, something that would accompany a large, a megaton, kiloton explosion, which would have sound waves that are more like blast waves like this. So it's going to be at least this loud. But when I say loud, like some other people do, this isn't loud like we know sound to be. It's more loud like an explosion is forceful. So start here and work your way up. What's next?
From Stephen Kearney, how would we live on Mars in the future?
Well, all easy questions. Let me just solve that problem so we can get to Mars ASAP. The big problem on Mars is there's almost no atmosphere. That's why landers on the red planet, if you wanted to land a robot on the red planet, for example, there's a wispy atmosphere. The sun blew it away. So when landers come in, they have to, instead of coming in directly down and hoping the air can slow you down, even if it's a decent angle, but you hope the air slows you down. That's what we do here on Earth. But because there's not a whole lot of air here, they have to take these weird, very long paths to slow down in the atmosphere quite a bit. So that is just one of the examples of the problems that a tiny, wispy, it's not tiny, a very undense atmosphere brings with it. And because of that, it's hard to breathe. There's not a lot of oxygen. So that's why people talk about terraforming Mars, making it more like Earth, or hoping to give it more atmosphere so it can retain heat, so it's not so cold, so we can actually breathe, so we can slow down and speed up in it effectively and fly around like we do here on Earth. That is one of the biggest main problems. Not only that, because there's not a whole lot of atmosphere here, there's a lot of radiation on the surface that gets through. Right now, well, I mean, I'm in a shapeless, formless, emotionless void, but for most of you on Earth's atmosphere and the magnetic field around Earth help to steer away and absorb a lot of the radiation that comes in from outer space and the sun. Mars does not do that nearly as well. So you have radiation problems, you have atmosphere problems, it is really cold, there's not water like there is here on Earth. It would be very, very hard to grow food. You'd probably need to ship in people's oxygen like they do for belters in The Expanse, beltalotas. So yes, as I've heard some environmental scientists say, Mars is not Plan B. It is a very hard problem. We're not going to escape to Mars anytime soon. It's going to take, we probably will not be living there in significant numbers by the end of my lifetime. But who knows how long that will be. Next question before I get depressed.
From Kirill. How do the ring gates in Expanse work?
Oh, dang. Okay. I don't work for The Expanse, but you should be watching The Expanse. It is the best sci-fi show on TV, and this week's episode, I won't spoil anything, but it involves a giant ring in space, and some really, really interesting physics happen when things get near this ring. And this week's episode, it ends with this really interesting thing happening near the ring, and you're like, what? So I'm not gonna say how they work, because I do not know how they work. Because, you can take liberties in these stories, and I don't want to spoil anything. So what I will say is go watch The Expanse. It just got renewed by Amazon. I was sitting next to the lead actor, Stephen Strait, when it got renewed by Jeff Bezos in the same room, and they were over the moon, metaphorically speaking, about the renewal of the show, because they love making it and I love watching it. I don't work for The Expanse, but you should watch it. What's next? Or put me on it. Then I can stop talking about it. No, I'd continue to talk about it. What's next?
From Zachary Ott. Hi, Kyle. I'm a longtime fan of your show.
Oh, hey, Zach, Uri.
In your episode on realistic space battles,
yes,
could ships sink their heat into conductive materials and launch them at opposing ships?
Oh, interesting. Weaponize your heat sinks. Well, if you go to any of my space-related episodes, you can see a lot of comments from a super nerd that I rely on sometimes for this kind of stuff called Matterbeam, and he, she, they could help you out with that if you go to ToughSF, at ToughSF on Twitter. He, she, they have written a lot about that. But what I will say is that heat management in space is absolutely critical, and I like where your head's at. You would need something like heat sinks, especially if you want to make something like stealth work in space, because there is no, there's nothing to block your radiation in space. Not really, if you're in empty space. People can see you pretty much everywhere if you're doing anything. So, we could detect you turning on your engine if we're on Earth and you were at Pluto. So stealth is hard in space. So you'd want something like a heat sink to draw the heat down into it. There's a heat gradient. Heat wants to travel to places of lower heat. It flows down into the heat sink, and then you could absorb that. So like a stealth ship could have armor that redirects the heat that's being generated by the ship down away from the armor, so it doesn't have so much of a heat signature, and then you could, I guess, eject that heat sink, but then it's gone and you can't use it again. You could use the heat sink and then go to a safe space and let it radiate away into space and then continue to use it. I guess you could use it as a weapon, but there are probably more efficient ways to go about doing that. If you want to use something that's really hot and metal to destroy something, get a railgun. What's next?
From Thomas O'Donnell. Does a lightsaber get heavier once it's switched on, or does the weight only come from the hilt?
Oh no. Okay, so here's the thing. lightsabers change, and their weight will change depending on your interpretation of what a lightsaber is and what it does and how it works, where and when, and all this stuff. It gets very complicated. That is why it is hard to do lightsaber episodes. So if you interpret a lightsaber as just being kind of like a hot stick that can burn through some stuff, then there doesn't have to be as much I consider it to be plasma inside of a magnetic field. There doesn't have to be as much plasma, doesn't have to be very dense, and so it could just weigh as much as a few grams of gas. Like the plasma that we use in experimental fusion reactors is just a few grams, and it gets up to millions of degrees inside of these fusion reactors. So if a lightsaber was doing something like that, it would be a few grams, and then the majority of the mass would be, in fact, in the hilt, and that would change the way that you actually used a lightsaber. If you think about it, all sword techniques ever account for the weight of the blade. It determines how you move your body. But if you are just basically moving around a hilt, then the blade can do much more nimble things, and because there's no edge, every edge is a cutting edge. That changes the way you use the lightsaber as well. That is one interpretation. Another interpretation is that if the lightsaber needs to get through something like a blast door, like in the Phantom Menace, then it needs a lot more mass of plasma in here, because that's gonna be able to transfer more heat energy. So, if you have a lot of plasma, very dense, combined, kind of corralled by a very, very strong magnetic field, then the blade can end up being very, very, very heavy indeed. So it depends on what you want a lightsaber to do. If you want it to look cool, not do much else, then it could be incredibly light. But if you want some industrial blast door cutting, it's gonna be heavy, like a real sword. How much heavier than a real sword? That sounds like an episode. So, I'll figure it out later. What's next?
From Atchison Mapping, how much energy would it take to pull a planet?
All easy questions today. Pull a planet. Now, how am I going to interpret what you interpreted that to interpret to mean? Everything in space is falling around something else. Whether that be a moon around a planet, whether that be a planet around a star, whether that be stars around a galactic core, whether that be a galactic core around a cluster of galaxies, whether that be space itself. Everything is always falling towards something else. Nothing in space is really stationary, which is weird to think about. So, pull a planet how? From a relatively speaking stationary frame? Like, what if you stop the Earth? How hard would you have to pull it to get it moving again? Well, then you could just do a simple equation where you take Newton's second law, force equals mass times acceleration, and you determine how fast you want to get the Earth moving, and then you factor in the mass of the Earth, which I have already written up here. So, 10 to the 24. That's a trillion multiplied by what? Even if you're doing 1 meter per second, you're talking about trillions, 6 trillion newtons. More than a feeling. No, more than anything has ever produced here on Earth in terms of force, I think. So, a lot is the answer to your question. But it depends on your frame of reference. Everything on Earth, everything in the universe, rather, is being pulled towards something else. Always. Gravity's clutches know no bounds. Everything is pulling on everything else at all times. You are always the factor in something's equation. Ooh, what's next? It's trying to be fakely profound. It worked out.
From Inetchable, where do comets come from?
Comets, I'm not an astronomer. if you didn't know. But I believe comets can either be captured from outside of the solar system or have or bodies that fall in from asteroid belts and things like that. But for more specifics, I think talk to Neil. He loves engaging with you on Twitter. He does. He got really mad at me once. What's next?
From Antimatter Beam.
What? There's an antimatter beam now? For those of you who don't know, right before we launched the Because Science channel, with one of my first videos, I contacted a group of super nerds who kind of do the same thing that I do, but they all do it in their spare time. They have regular jobs, and they get way into it. And I contacted one named Matterbeam, and he, she, they has helped out with a number of calculations through a number of episodes very generously. So he, she, they are featured in comment sections a lot and stuff like that. Now this is an antimatter beam. I don't even know who Matterbeam really is, and now you have a nemesis. Anyway, what does it say?
Antimatter Beam asks, if me and Matterbeam got to hang, would the Earth survive?
The Earth would survive if you and Matterbeam touched each other. There's two answers to this question. I'm going to go with the more interesting one. Now, in pop culture like Star Trek or in Angels and Demons, that amazingly well-written book, don't laugh, there are antimatter bombs, and it uses the fact that, oh, look at this, uses the fact that energy and matter are related. So if you combine two particles of opposite charge, the same particle, they just have a different charge, matter beam and antimatter beam, then they release energy according to their mass, according to E equals mc squared. So you take their mass, you multiply it by the speed of light squared, you get an energy value. Now, the easy answer to your question would be to take the average mass of two people and add them together and multiply it by c squared. And then you would get your energy value. But it's more complicated than that, because to get an antimatter bomb to explode, you would want all of the particles to react to each other simultaneously. And you just know that that is not going to really happen in the real world. If you brought an antimatter person that was the opposite of you into contact with yourself, like if my hand was touching an antimatter hand here, once the very first layers of our hands touched, it would create an incredible explosion. Even just a few grams in a matter-antimatter annihilation reaction is an incredible amount of energy released. And that incredible amount of energy released would blow away the two matter-antimatter people as if a giant bomb went off in between them, and so not all of the matter-antimatter would react. So this equation, when people do the matter-antimatter sci-fi stuff, it's a little misleading because you're assuming perfect mixing of every single atom in that object that you are reacting with antimatter, when in reality, just touch the surfaces of two things together and they're gonna blow each other up way apart. And if you want to get even more complicated, even if an antimatter person was touching air, explosions would happen. So it gets very, very complicated. So the cool answer is if antimatter beam and matter beam, the people, touched their hands together, the Earth would survive because it wouldn't be as big of an explosion as you expect, even though it would be pretty spectacular, because they would not fully react. I mean, they'd be dead, but not all of us. What's next?
We have time for two quick questions.
Two quick questions.
From Fran, Goriki. What is the hardest question you had to solve?
You know what? It sounds silly, but the hardest episode of the show I've ever worked on wasn't anything to do with math. My goal as a science communicator, and because of my background, I don't have a PhD, I don't do research. I have a background in science, I have a degree, but I stick to what I know. So what I want to do is to introduce very basic science and engineering concepts, basic math, to hopefully get people interested to learn more complicated stuff. So I usually stick to math that is in my wheelhouse. So the episodes with math are usually okay. The hardest episode I ever had to do is also my longest episode, where I tried to put every xenomorph on a family tree together. What makes what, and how, and when, and with what? How does the goo make the predalien make with the queen, and does the egg and the face hugger? I had to look through interviews with every director of every Alien film and what their interpretation of the creature's life cycles were, and put that all together. And it's a 19-minute video, I think, on Nerdist's YouTube channel, if you want to look it up. And I almost lost my dang mind doing it. I had 6 full pages of notes. A typical episode of Because Science, even though I write super tiny, I'm told like a psychopath. Most episodes of Because Science fit on a single sheet of paper. This one took 6. That was my hardest. We have time for one more quick one?
Yeah.
Cool.
From Julia Greenleaf.
Hey.
Hi, just wondering, what got you into science?
What got me into I was a couple things. I was very, very fortunate that my parents encouraged me to be curious. They got me Legos. They took me to museums. They got me dinosaur CD-ROMs. They let me just kind of not really like kids today, as far as I can see. They can just let me out into the backyard with a microscope, and not a microscope, with a magnifying glass to look at bugs and to catch frogs down by the pond and stuff like that. I was in my own little world, always being curious. And then going through school, I was very fortunate to have great teachers at every level, from my 8th grade science teacher, Mr. D, all the way through high school and college. And so I think I've always been into science, or at least the way that science works and how it interrogates the universe. But I've been lucky in that people have always been there to encourage me and to support me. And now, because I feel like I've been so lucky, I feel like I am obligated to, if I can, do the same for all of you. And that's what I try to do every week here. Sometimes it turns out all right. That's all the time we have for today. That's another episode of Because Science Live. Make sure to tune in next week. We have another vlog on this channel. We have another main episode. We have, did I say what the main episode is? Nope. We have another episode of Because Science Live, so leave your comments, questions, reactions to everything across all of our platforms. We have youtube.com/BecauseScience, facebook.com/BecauseScience, and at Because Science on Instagram and Twitter. And get in there, be nerdy, and be nice to each other. Because, I'll tell you, I think about this all the time when I'm floating here in this shapeless, formless, emotionless void. This is all we got. So be nice.